So in this video, we're going to put it all together. So there's been a lot of things to keep track of. So I think this video is very important to kind of tie everything together. So we have to be able to take a cell and calculate the cell voltage from standard electrode potentials and write the overall chemical equation. So for instance, here is a cell, and I'm going to use the cell notation. And what I like to do in this video is show you how to calculate the cell voltage and how to calculate the overall chemical equation. So, of course, the cell diagram right allows us to avoid drawing out a picture of a cell, but I think at this point you should probably be able to sketch this out. And how do we calculate the cell voltage here? So we're going to go ahead and we're going to say that the way it's written, the cell voltage, is equal to the right-hand side minus the left-hand side. And if you remember, the right-hand side is the cathode, and the left-hand side is the anode. So all we need to do is we need to look up these standard electrode reactions that involve the gold 3 going to gold and the silver 1 going to silver. And they'll always be written as reduction reactions. So let me pull up the table and show you. Now, instead of pulling up the full table, I've just kind of clipped out the electrode reactions that we need. And this is sort of like playing Where's Waldo. So you have to find, so there's the gold 3 and there's the gold. You have to find the reaction that converts gold 3 and gold. And then there's the silver and silver ions. So there's silver ions and silver. Notice that reaction is written as a reduction. However, at this electrode here, it's actually taking place as an oxidation, because oxidation takes place at the anode, reduction at the cathode. Remember, red cat and an ox. So how do we do this? So the first thing that people want to do is they want to flip one of the reactions around and flip the voltage, and that is never a good idea. So don't be tempted to do that. So here's my cathode. So my cathode is on the right. So notice alphabetically anode comes before cathode. That helps us remember. And the cathode reaction is gold 3 going to gold. So that's this one right here. And it's got a voltage of positive 1.5. So that's a very favorable reaction. On the left-hand side, we've got the silver going to silver ion, so that is oxidation. And I didn't mention this earlier, but you can often think about these reactions as proceeding from left to right, where you've got a phase boundary like so. So that is this reaction here. And notice we tabulate it as a reduction, but we don't change that voltage. So we just subtract positive 0.80, and that subtraction, if you like, essentially flips the sign. And I think I can do that in my head, actually. I think that's positive 0.70 volts. So it is positive. So that means that it is favorable. That means that essentially the reaction proceeds as written. And if we ever calculate a negative voltage just means the reaction is not favorable forwards. It just means that it's favorable backwards. So if we got E cell less than 0, it would mean the reaction proceeds in the opposite direction. However, if we get E cell greater than 0, it means the reaction is spontaneous in the forwards direction. So if we get a negative voltage, it just means our anode and our cathode is actually switched around. So that is pretty awesome. And what about the cell reactions and the overall chemical equation? It takes a little bit more work. So we know that the silver is being oxidized. Okay, that's the reaction that takes place at the anode. Anode is where oxidation takes place. So we are essentially reversing that second equation. The gold is being reduced. So it is grabbing 3 electrons from the silver side and turning it into gold. Some people write these as equilibrium. Sometimes we just write arrows. We'll have to remember it's always an equilibrium, but it's easier to write an arrow sometimes. We would really love to add these equations together, but remember, we're balancing redox equations here. So actually, these are kind of simple because they don't have oxygens or hydrogens messing things up. So everything is kind of pre-balanced, but we've got 1 electron here. We've got 3 electrons here. So if we added them up, we'd get 2 leftover electrons. So remember from the balancing chapter, we said that you've got to multiply these by factors to cause the electrons to cancel out. So if I multiply that one by 3, that will actually give me 3 electrons on each side. So they would cancel, which is exactly what we want. So now we get 3 silvers plus 1 gold 3 positive. And I like to write my 3 electrons over the arrow because we're going to use those in a second, even though that they don't really belong in the equation. That's useful information. And we tripled the first one, so we don't have 1 silver. Oops, we have 3 and we just multiply the second one by 1, so we just have 1 gold. So we can just double check this is balanced. So 3 silvers, 1 gold, 1 gold. Charge is 3 positive, charge is 3 positive, so that is about as balanced as it gets.